Welcome to The Drowsy Astronaut, where we follow journeys through space that unfold slowly, one quiet detail at a time, and tonight we travel with humanity's most distant ambassadors, the Voyagers. This will be a long story, spread across many hours, so if you are here to relax, to focus on something else in the background, or simply to fall asleep, then you are exactly where you need to be. Just know that there is no rush, no test, no need to remember every fact, because the Voyagers are still traveling, moving farther from Earth with every second that passes. This video will carry you through the solar system and beyond, following two spacecraft that left Earth in 1977 and that are still traveling today, farther than any human-made object has ever gone. We will trace the full arc of its journey, past Jupiter and Saturn, through the cold realms of Uranus and Neptune, and beyond the edge of the Sun's domain into the interstellar medium. I will keep the language simple, the pace unhurried, and the science steady, so you can do what you intend, while drifting beside Voyagers into the great unknown. And lastly, I would love to know where you are listening from, whether you are under clear skies or city lights, in bed, at work, or somewhere peaceful between the two. Drop a comment if you're comfortable sharing, and without further ado, let us begin here on Earth. In the summer of 1977, when two identical spacecraft were prepared for launch, carrying a message from humanity into the unknown cosmos. These spacecraft were called Voyager 1 and Voyager 2, and they were designed to explore the outer planets, Jupiter, Saturn, Uranus, and Neptune, taking advantage of a rare alignment that happens only once every 176 years. That alignment meant the spacecraft could use gravity assists, swinging past each planet and gaining speed, allowing them to visit all four giant worlds in a single journey that would otherwise take decades longer. But the mission was more than exploration. It was also a message, a greeting, a statement that intelligent life exists in the universe and that we are curious about what lies beyond our world. Each Voyager carried a golden record, a 12-inch gold-plated copper disc, containing sounds, images, and music from Earth, selected by a team led by the astronomer Carl Sagan. The record was designed to last billions of years, protected by an aluminum cover with instructions engraved in symbols, showing how to play it and where it came from, assuming someone or something finds it. The contents were chosen to represent the diversity of life on Earth, including greetings in 55 languages, natural sounds like thunder, wind, and animal calls, and music ranging from Bach to Chuck Berry. There were also 115 images, encoded as audio signals, showing scenes of Earth, human anatomy, mathematical definitions, and the solar system, a visual encyclopedia of our planet and its inhabitants. The sounds included a baby crying, a mother's kiss, footsteps and laughter, all the small, intimate noises of human life, the things that make us who we are, captured in audio and sent into space. There were also sounds of technology, a train, a car, a rocket launch, and the voice of then Secretary General of the United Nations, Kurt Waldheim, offering greetings on behalf of the people of Earth. The music spanned cultures and centuries, from Beethoven's Fifth Symphony to traditional music from Java, Peru, and Japan, each piece chosen to represent humanity's creativity and emotional depth. The record was a message of hope, sent into the void with no expectation of reply, a statement that we exist, that we create, and that we wonder about the universe beyond our small blue world. The instructions for playing the record were etched onto the aluminum cover, using universal symbols that any intelligent species might understand, including a diagram of a hydrogen atom and the position of the Sun relative to nearby pulsars. The pulsars act as a cosmic map because their rotation periods are unique and measurable, allowing anyone who finds the record to determine when and where it came from, even billions of years in the future. The cover also included a stylus for playing the record, and diagrams showing how to decode the images and audio, though whether any future finder will understand these instructions remains an open question. But the effort itself was meaningful. The act of trying to communicate across time and space, sending a message with no guarantee it would ever be received, let alone understood. Voyager 2 launched first on August 20th, 1977 from Cape Canaveral in Florida, riding atop a Titan rocket that carried it beyond Earth's atmosphere and into the darkness beyond. Voyager 1 followed 16 days later on September the 5th, taking a faster trajectory that would allow it to reach Jupiter and Saturn before its twin, despite launching second. Both spacecraft were identical, weighing about 820 kilograms each, with a large dish antenna for communicating with Earth, a suite of scientific instruments, and a nuclear power source called a radioisotope thermoelectric generator. The RTG converts heat from decaying plutonium into electricity, providing power for the spacecraft's systems, and it was designed to last for decades, far longer than solar panels could function in the dim light of the outer solar system. The spacecraft left Earth behind, climbing away from the pull of gravity, passing the Moon's orbit within hours, and entering the vast emptiness between Earth and the first stop on their journey, the giant planet Jupiter. The journey to Jupiter would take nearly 2 years, crossing hundreds of millions of kilometers, and during that time, the spacecraft tested their instruments, sent data back to Earth, and drifted through the asteroid belt without incident. The asteroid belt is not as dense as movies suggest. The rocks are spread out over vast distances, and the chance of hitting one is extremely low, though mission planners tracked the spacecraft carefully to ensure they stayed on course. As Voyager traveled, Earth shrank behind it, becoming first a bright star, then a faint point of light, and finally invisible, lost in the glare of the sun, a reminder of how far the spacecraft had come. The mission team on Earth stayed in constant contact, sending commands to the spacecraft and receiving data in return, though the signals took longer and longer as the distance grew, eventually reaching tens of minutes for a one-way transmission. The Deep Space Network, a collection of large radio dishes, located in California, Spain, and Australia, tracked the spacecraft around the clock, ensuring no data was lost and no command went unheard. The engineers and scientists who built Voyager knew the spacecraft would outlive their careers, and perhaps outlive humanity itself, continuing to travel long after we are gone, carrying the golden record into the unknown future. But for now, in 1977, the focus was on the planets, on the discoveries that awaited, and on sending back images and data that would change how we understand the outer solar system. Imagine standing on Earth, looking up at the night sky, and knowing that somewhere out there, moving faster than any bullet, 2 small machines carry your voice, your music, and your image into the darkness. They travel at about 17 kilometers per second, fast enough to cross the United States in less than 5 minutes, and they will never stop, never turn around, and never return to Earth. The golden record is sealed inside, protected from the cold and radiation of space, waiting for a finder that may never come, or that may discover it millions of years from now in a galaxy we cannot imagine. That record is humanity's handshake across time, a greeting sent with hope, with humility, and with the simple desire to say we were here, we lived, and we reached out into the cosmos. The launch was the beginning, the first step of an endless journey, and as Voyager left Earth behind, it carried not just instruments and data, but the dreams and curiosity of everyone who had looked up and wondered what lies beyond. And now, more than 45 years later, the spacecraft are still traveling, still sending signals back to Earth, though those signals grow fainter with each passing year and the power is slowly running out. But tonight, we follow them, retracing their path through the solar system, past the giant planets, beyond the edge of the sun's influence, and into the interstellar void where they will drift forever. So rest now and let the story unfold, slowly, gently, one discovery at a time, as we travel with Voyager toward the stars. Voyager 1 reached Jupiter on March 5, 1979, after traveling for more than 18 months through the cold vacuum of space, and what it found there exceeded every expectation. Jupiter is the largest planet in our solar system, more massive than all the other planets combined, and its colourful bands of clouds, swirling storms, and enormous magnetic field make it one of the most dynamic worlds we know. The spacecraft approached from below the planet's equator, sending back the first high-resolution images of Jupiter's atmosphere, revealing details far sharper than any telescope on Earth could capture. And scientists watched in awe as each picture arrived. The images took minutes to transmit, built up line by line, and when they were complete, they showed a world more complex and beautiful than anyone had imagined, with eddies, waves, and storms painted across the giant planet's face. The Great Red Spot dominated the southern hemisphere, a storm larger than Earth, spinning counterclockwise and lasting for centuries, and Voyager's cameras revealed its structure in stunning detail, showing smaller storms being absorbed and clouds swirling at its edges. The spot is not a solid feature. It is a high-pressure storm, a hurricane that never makes landfall, and it has been observed from Earth for at least 300 years, though it may be much older. Voyager measured the winds around the spot, finding speeds exceeding 400 kilometers per hour, and it watched the storm rotate once every 6 days, a massive engine of atmospheric energy powered by heat from Jupiter's interior. The colors of the spot, reds and browns, come from complex chemistry in Jupiter's clouds, possibly involving sulfur and phosphorus compounds, though the exact composition remains uncertain, and scientists are still debating the details decades later. Beyond the Great Red Spot, Voyager discovered dozens of smaller storms, white ovals and brown barges that drift through the atmosphere, some lasting for years, others forming and dissipating within months. Jupiter's atmosphere is divided into bands, light zones and dark belts, created by winds that blow in opposite directions, and the boundaries between them are turbulent regions where storms form and energy is released. The winds are driven by Jupiter's rapid rotation, one full turn every 10 hours, and by heat rising from the planet's interior, which is still warm from the energy of its formation billions of years ago. Voyager also measured Jupiter's magnetic field, finding it 20,000 times stronger than Earth's, and it discovered that the field traps charged particles, creating radiation belts far more intense than any in our solar system. But Jupiter was not the only discovery. The planet is surrounded by a family of moons, 4 large ones discovered by Galileo in 1610, and many smaller ones found more recently, and Voyager studied them all in unprecedented detail. Io, the innermost large moon, turned out to be the most geologically active body in the solar system, with active volcanoes spewing sulfur compounds hundreds of kilometers into space, painting the surface in yellows, oranges, and reds. The volcanoes were a complete surprise. No one expected a moon to be active, especially one so small, but the tidal forces from Jupiter's gravity heat Io's interior, melting rock and driving the volcanic eruptions continuously. Voyager 1 captured images of erupting plumes rising above Io's limb, and scientists realized they were watching volcanism in real time, a dynamic world constantly reshaping its surface through fire and sulfur. Europa, the next moon outward, looked completely different, covered in smooth ice with very few craters, suggesting the surface is young, constantly renewed by processes hidden beneath the frozen crust. The ice is crisscrossed with cracks and ridges, giving Europa a fractured appearance, and the lack of craters means the surface is geologically active, though the mechanism remained unclear from Voyager's distant observations. Later missions would confirm what Voyager hinted at, that beneath Europa's ice lies a global ocean of liquid water, kept warm by tidal heating and possibly home to the conditions necessary for life. But in 1979, Europa was simply a beautiful mystery, a smooth white moon with strange markings, and scientists knew they would need to return for a closer look. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury, showed a mix of dark ancient terrain and bright grooved regions, indicating a complex geological history. The grooved terrain suggested tectonic activity, possibly driven by internal heating, and the contrast between the dark and light regions revealed a world with multiple episodes of surface renewal. Callisto, the outermost large moon, was heavily cratered, one of the most ancient surfaces known, and it appeared geologically dead, a frozen remnant from the early solar system, untouched by the tidal forces that heat Io and Europa. Together, the 4 Galilean moons showed an astonishing diversity, from volcanic Io to icy Europa, from grooved Ganymede to ancient Callisto, and each one told a different story about how moons form and evolve. Voyager 1 also discovered a faint ring around Jupiter, barely visible against the planet's glow, made of tiny dust particles probably knocked off the inner moons by micrometeorite impacts. The ring was a surprise, because astronomers had not expected Jupiter to have rings, though Saturn's magnificent ring system was already well known, and the discovery suggested that rings might be common around giant planets. The spacecraft passed through Jupiter's intense radiation belts, where high-energy particles bombarded its instruments, and engineers had designed the electronics to withstand the assault, though some systems were damaged and had to be reset remotely from Earth. Despite the challenges, Voyager 1 completed its mission, sending back thousands of images and measurements, and after its closest approach, it used Jupiter's gravity to accelerate towards Saturn, the next stop on its grand tour. Voyager 2 arrived at Jupiter 4 months later, in July 1979, following a similar trajectory, but focusing on different targets. And it confirmed Voyager 1's discoveries while adding new details and observing changes in the atmosphere. The Great Red Spot had shifted slightly, and the smaller storms had evolved, showing that Jupiter's atmosphere is constantly changing and that any snapshot is just a moment in an ongoing dynamic process. Voyager 2 studied the moons again, capturing images from different angles, and it watched Io's volcanoes erupt, confirming that the activity was continuous and widespread, not a rare event captured by chance. Together, the two spacecraft revolutionized our understanding of Jupiter, transforming it from a distant dot of light into a real world with weather, moons, rings, and a dynamic environment more complex than anyone had imagined. As Voyager 1 left Jupiter behind, accelerating towards Saturn, the planet shrank in the rear cameras, becoming smaller and smaller until it was once again a bright point of light, indistinguishable from the stars. But the data kept coming back to Earth. Scientists pored over the images and measurements, writing papers, making discoveries, and planning for the next encounter, which would take place 18 months later at the ringed giant. Jupiter had been a triumph, exceeding all expectations, and the spacecraft had performed flawlessly, surviving the radiation, capturing the images, and using gravity to accelerate toward the next planet, proving that the grand tour was possible. The journey continued, the spacecraft drifting through the darkness, silent and alone, carrying the golden record farther from Earth and approaching the most beautiful planet in the solar system. Voyager 1 reached Saturn on November 12, 1980, after a journey of more than 3 years from Earth, and what awaited was a spectacle of rings, moons, and atmospheric beauty unlike anything else in the solar system. Saturn is the second largest planet, and it is famous for its rings, visible even through small telescopes from Earth, but Voyager revealed those rings in breathtaking detail, showing thousands of individual ringlets, gaps, and waves that had never been seen before. The rings are made mostly of water ice, chunks ranging from tiny grains to house-sized boulders, all orbiting Saturn in a thin disk only tens of meters thick in most places, though the rings span hundreds of thousands of kilometers across. Voyager's cameras captured the rings from angles impossible from Earth, edge-on, backlit by the sun, and from above, revealing structure after structure, a complexity that scientists are still working to fully understand decades later. The rings are divided into major sections labelled A, B, and C, with gaps like the Cassini division separating them, and Voyager discovered that even these gaps contain fainter rings, making the system far more intricate than anyone had expected. The particles in the rings are shepherded by small moons, which orbit within or near the rings and use their gravity to keep the particles confined, creating sharp edges and preventing the rings from spreading out over time. Voyager discovered several of these shepherd moons, tiny objects only a few kilometers across, invisible from Earth, but essential for maintaining the ring structure, and their discovery explained how Saturn's rings could be so thin and well-defined. The rings also showed waves and spiral patterns, created by gravitational resonances with Saturn's larger moons, and these patterns revealed the delicate balance of forces that keeps the ring system stable over millions of years. Saturn itself is a gas giant like Jupiter, but its atmosphere is calmer, with fewer storms and fainter cloud bands, giving it a more uniform appearance, though Voyager still found wind speeds exceeding 1,500 kilometers per hour. The planet rotates quickly, completing one turn in just over 10 hours, and this rapid rotation flattens the planet noticeably, making its equatorial diameter about 10% larger than its polar diameter. The colors of Saturn are muted compared to Jupiter, pale yellows and creams, because a high-altitude haze obscures the deeper cloud layers, and the chemistry in the atmosphere is dominated by ammonia and methane rather than sulfur compounds. Voyager measured Saturn's magnetic field, finding it weaker than Jupiter's but still significant, and it discovered that the field is almost perfectly aligned with the planet's rotation axis, an unusual configuration that scientists are still trying to explain. The spacecraft also studied Saturn's moons, a diverse collection ranging from tiny captured asteroids to giant Titan, larger than the planet Mercury, and each moon revealed surprises that hinted at hidden complexity beneath their frozen surfaces. Titan was the main target for Voyager 1, and the spacecraft passed within 6,000 kilometers of the moon's surface, closer than it approached Saturn itself, because scientists wanted to study Titan's thick atmosphere. Titan is the only moon in the solar system with a dense atmosphere, thicker than Earth's, composed mostly of nitrogen with traces of methane and other organic compounds, and the surface is completely hidden beneath orange smog. Voyager's instruments measured the atmosphere's composition, and they found that the pressure at the surface is about 50% higher than Earth's sea level, making Titan more like a planet than a moon in some ways. The temperature at Titan's surface is extremely cold, about minus 180 degrees Celsius, cold enough for methane to exist as a liquid. And scientists speculated that Titan might have lakes or seas of methane, though Voyager's cameras could not see through the haze to confirm it. Later missions would indeed find liquid methane on Titan, lakes and seas near the poles, and a hydrological cycle similar to Earth's water cycle, with methane rain, rivers, and evaporation. A parallel world operating under completely different chemistry. But in 1980, Titan was a tantalizing mystery. Its surface hidden, its atmosphere thick and complex, and scientists knew they would need another mission to reveal what lies beneath the orange clouds. Voyager 1's trajectory was designed to pass close to Titan, and that close approach changed the spacecraft's path, bending it upward out of the plane of the solar system and ensuring it would never visit another planet. After Titan, Voyager 1 studied other moons of Saturn, including Mimas, Enceladus, Tethys, Dione, Rhea, and Iapetus, each one revealing a different aspect of how icy moons form and evolve. Mimas has a giant crater, Herschel, 1/3 the diameter of the moon itself, and the impact that created it nearly shattered Mimas, making it a testament to the violence of the early solar system. Enceladus looked smooth in places and heavily cratered in others, suggesting recent geological activity, though Voyager's distant images could not resolve the details, and the full story of Enceladus would have to wait for later missions. Iapetus is two-toned, one hemisphere bright white, the other dark as coal, and Voyager's images showed the sharp boundary between the two regions, a mystery that still puzzles scientists, and may involve material falling onto the moon from elsewhere in the system. Voyager 2 arrived at Saturn 9 months after Voyager 1, in August 1981, and it focused on targets that its twin had missed, including more detailed studies of the rings and closer passes by some of the moons. Voyager 2 confirmed that the rings are even more complex than Voyager 1 revealed, with braided rings, kinked rings, and structures that seem to defy the laws of orbital mechanics, at least until scientists worked out the gravitational interactions causing them. The spacecraft also studied Saturn's magnetosphere, the region where the planet's magnetic field dominates, and it found that the magnetosphere is distorted by the solar wind, stretched into a long tail on the side away from the Sun. Together, the two voyages transformed our understanding of Saturn, revealing it as a dynamic system with active moons, complex rings, and an atmosphere shaped by powerful winds and subtle chemistry. As Voyager 1 climbed away from Saturn, its trajectory carried it above the plane of the solar system, and it would never encounter another planet. Its mission now focused on studying interstellar space and the edge of the Sun's influence. But Voyager 2 continued onward, using Saturn's gravity to accelerate toward Uranus, the next planet on its grand tour, and the mission was far from over, with 2 more giant worlds still to explore. The images from Saturn continued to pour in for weeks, and scientists analyzed every detail, discovering new moons, new ring structures, and new mysteries that would take decades to fully understand. Saturn had been a triumph of beauty and complexity, its rings a testament to the delicate balance of gravity and motion, and Voyager had captured it all, sending the data across billions of kilometers back to Earth. Imagine drifting past Saturn, watching the rings stretch out below you. Thousands of individual ringlets catching the sunlight and the giant planet slowly rotating, its moons sweeping through their orbits like a celestial clockwork. The view would be silent because space carries no sound, but the sight would be overwhelming, a display of cosmic architecture built from ice, gravity, and time, and you would know that you are witnessing something rare and precious. Voyager carried that view back to us, encoded in radio signals, translated into images, and shared with the world, allowing everyone on Earth to see Saturn's majesty, even though the spacecraft was the only witness there. And then Voyager 2 moved on, leaving Saturn behind, accelerating toward Uranus and continuing the journey that would take it to the edge of the solar system and beyond. Voyager 2 reached Uranus on January 24, 1986, nearly 5 years after leaving Saturn, and what it found was a world unlike any other, tilted on its side and covered in a featureless blue-green haze. Uranus is the 3rd largest planet, and it orbits the Sun at a distance nearly 20 times farther than Earth, where sunlight is weak and temperatures plunge to -200 degrees Celsius, making it one of the coldest places in the solar system. The planet's most striking feature is its tilt. Its rotation axis lies almost in the plane of its orbit, so it rolls around the Sun like a ball, and its seasons are extreme, with each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness. No one knows why Uranus is tilted so dramatically, but the leading theory suggests a giant impact early in the planet's history, a collision with another planet-sized object that knocked Uranus onto its side and left it spinning in this unusual way. The atmosphere of Uranus is calm compared to Jupiter and Saturn, with few visible storms and a uniform colour that makes it difficult to discern any structure, and Voyager's cameras struggled to find features to track and study. The blue-green colour comes from methane in the atmosphere, which absorbs red light and reflects blue and green wavelengths, giving Uranus its distinctive appearance, though the atmosphere is mostly hydrogen and helium, like the other giant planets. Voyager measured the winds on Uranus, finding speeds up to 200 kilometers per hour, slower than Jupiter or Saturn, but still substantial, and the winds blow in the direction of rotation, driven by the planet's internal heat and the faint sunlight. The planet emits very little internal heat, unlike Jupiter and Saturn, which radiate more energy than they receive from the Sun, and this lack of internal heat may explain why Uranus's atmosphere is so calm and featureless. The magnetic field of Uranus is strange, tilted 59 degrees from the rotation axis and offset from the planet's center, and this unusual configuration creates a lopsided magnetosphere that wobbles as the planet rotates. Scientists are still unsure what causes this odd magnetic field, but it may be related to the way the planet's interior is structured, with the magnetic field generated in a thin shell rather than in a deep core like Earth's field. The magnetosphere interacts with the solar wind, creating a tail that stretches behind the planet, and Voyager detected charged particles trapped in radiation belts, though far weaker than Jupiter's intense belts. The tilt of the magnetic field means the magnetosphere wobbles wildly as Uranus rotates, and this wobbling creates a complex environment that scientists are still working to understand decades after Voyager's visit. Voyager also discovered new moons around Uranus, 10 small moons that had never been seen from Earth, bringing the total to 15 at the time, and each moon revealed clues about how the Uranian system formed and evolved. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were already known, and Voyager studied them in detail, finding surfaces shaped by impacts, tectonics, and possibly ancient cryovolcanism. Miranda was the most surprising, a small moon with a surface that looks shattered, with cliffs, canyons, and chaotic terrain suggesting a violent past, perhaps a collision that broke the moon apart and allowed it to reform. One of Miranda's cliffs, Verona Rupes, is the tallest known cliff in the solar system, 20 kilometers high, and if you fell from the top, it would take about 12 minutes to reach the bottom in Miranda's weak gravity. Ariel and Titania showed signs of past geological activity, with valleys, faults, and smooth plains that may have been resurfaced by ice flows, though the processes that created these features remain uncertain. Umbriel is the darkest of Uranus's large moons, heavily cratered and ancient, and it appears geologically dead, with no signs of the activity seen on its neighbours, making it a frozen relic from the early solar system. Oberon, the outermost large moon, is also heavily cratered, with some bright rays radiating from fresh impacts, and its surface is old and cold, untouched by the tidal forces that heat some of Jupiter's and Saturn's moons. Together, the moons of Uranus showed a mix of activity and quiescence, some shaped by internal forces, others frozen in time, and each one a small world with its own unique story. Voyager 2 also discovered that Uranus has rings, thin and dark, made of particles that reflect very little light, and they are much fainter than Saturn's spectacular ring system, but they are there, encircling the tilted planet. The rings were first detected from Earth in 1977, when Uranus passed in front of a star and the star's light dimmed briefly before and after the planet blocked it, revealing the presence of narrow rings. Voyager confirmed the rings and discovered additional ones, bringing the total to 11 at the time, and it found that the rings are narrow and dark, probably made of material left over from collisions between small moons. Shepherd moons, similar to those at Saturn, help confine the rings and keep them from spreading out, and Voyager discovered 2 of these tiny moons, Cordelia and Ophelia, orbiting just inside and outside the outermost ring. The encounter with Uranus was brief, just a few hours of closest approach, but Voyager 2 sent back thousands of images and measurements, revealing a world that had been almost completely unknown before the visit. Uranus had been a pale blue-green dot in telescopes, but Voyager transformed it into a real world with weather, moons, rings, and a magnetic field. And scientists realized that even the distant ice giants have complex and dynamic environments. After the encounter, Voyager 2 used Uranus's gravity to accelerate toward Neptune, the final planet on its journey, and the spacecraft continued onward, deeper into the cold outer reaches of the solar system. The next encounter would take more than 3 years, and during that time, Voyager would coast through the darkness, its instruments monitoring the space environment and its cameras, watching for anything unexpected along the way. Imagine being on Uranus's surface if it had a solid surface, looking up at a sky filled with faint sunlight, cold and blue, and knowing that the sun is so far away it appears only as a bright star. The horizon would tilt strangely because the planet is on its side, and if you were near the pole during the long summer, the sun would circle the sky without setting for 42 years. The atmosphere above you would be thick and cold, made mostly of hydrogen, helium, and methane, and the winds would blow steadily, driven by the planet's rotation and the faint warmth from the distant sun. You would be farther from Earth than almost anywhere in the solar system, and the cold would be absolute, more than 200 degrees below zero, a place where even nitrogen would freeze solid and fall like snow. Voyager saw Uranus for what it is, a lonely tilted giant rolling through the outer solar system, and it sent that vision back to us, allowing us to see a world that few had ever imagined in detail. The spacecraft moved on, leaving Uranus behind, and the planet returned to being a distant dot. But the data remained, the images, the measurements, and the knowledge that even the farthest planets are real places, not just points of light. And Voyager 2 continued, carrying the golden record farther from Earth, into regions where sunlight grows dim and the cold deepens, approaching the final planet, the last stop before interstellar space. Voyager 2 reached Neptune on August 25, 1989, after a journey of 12 years from Earth, and this final planetary encounter would be the mission's grand finale, revealing a world of storms, winds, and a moon unlike any other. Neptune is the fourth largest planet and the farthest from the Sun, orbiting at a distance 30 times greater than Earth, where sunlight is 900 times dimmer and temperatures drop to minus 214 degrees Celsius, colder even than Uranus. Despite the cold, Neptune is surprisingly active, with the fastest winds in the solar system, exceeding 2,000 kilometers per hour, and a dynamic atmosphere filled with bright clouds and dark storms. The planet's deep blue color comes from methane in the atmosphere, but Neptune is bluer than Uranus despite having similar atmospheric composition. And scientists suspect there is an additional unknown component that deepens the color. The most striking feature Voyager discovered was the Great Dark Spot, a storm system roughly the size of Earth, spinning counterclockwise in Neptune's southern hemisphere, similar to Jupiter's Great Red Spot but darker and more transient. The dark spot was surrounded by bright white clouds, high-altitude methane ice crystals that formed as gas rose and cooled, and these clouds moved around the spot like companions, changing shape and brightness over hours. Voyager measured the winds around the Great Dark Spot, finding speeds exceeding 1,500 kilometers per hour, and it watched the storm drift westward relative to the planet's rotation, a sign of complex atmospheric dynamics. Later, observations from Earth revealed the Great Dark Spot had vanished by 1994, only 5 years after Voyager's visit, and new spots have appeared and disappeared since, showing that Neptune's atmosphere is constantly changing. The winds on Neptune are the fastest in the solar system, driven by internal heat that Neptune radiates into space, and this internal heat source makes Neptune more active than Uranus, even though both planets are similar in size and composition. Scientists are still unsure what powers Neptune's internal heat, but it may come from gravitational contraction as the planet slowly shrinks, or from chemical processes deep in the interior, or from heat left over from the planet's formation. The atmosphere shows bands of clouds, similar to Jupiter and Saturn, but the bands are fainter and less defined, and the clouds are made of methane ice at high altitudes and ammonia compounds deeper down. Voyager also detected small, bright features, nicknamed scooters, because they moved quickly across the planet, and these features may be plumes of gas rising from deeper layers, though their exact nature remains uncertain. Neptune has a magnetic field similar to Uranus, tilted 47 degrees from the rotation axis and offset from the center, creating a complex, lopsided magnetosphere that wobbles as the planet rotates. The similarity between Neptune's and Uranus's magnetic fields suggests this configuration may be common for ice giants, and it probably reflects the internal structure of these planets, with the field generated in a thin shell of conducting material. The magnetosphere interacts with the solar wind, creating a bow shock, and Voyager detected charged particles trapped in radiation belts, though they are much weaker than Jupiter's belts and pose little threat to spacecraft. Neptune's magnetic field also interacts with Triton, its largest moon, and the moon's atmosphere is stripped away by the magnetosphere, creating a plasma trail that Voyager detected as it flew past. Triton was the highlight of Neptune's encounter, a large moon orbiting in the opposite direction to Neptune's rotation, suggesting it was captured by the planet's gravity rather than forming alongside it. The moon's retrograde orbit is slowly decaying, meaning Triton is spiraling inward, and in about 3.6 billion years it will cross Neptune's Roche limit, where tidal forces will tear it apart, creating a spectacular ring system around the planet. Voyager passed within 40,000 kilometers of Triton, closer than it approached Neptune itself, and the spacecraft sent back stunning images of a world with a thin nitrogen atmosphere, geysers erupting from the surface, and a landscape shaped by exotic ices. Triton's surface temperature is minus 235 degrees Celsius, making it the coldest surface measured in the solar system, and at these temperatures nitrogen is solid and methane forms frost that covers the icy terrain. The geysers on Triton were a complete surprise. Plumes of nitrogen gas erupting from beneath the surface, rising up to 8 kilometers high before being blown sideways by Triton's thin winds, creating dark streaks across the icy plains. The geysers are probably driven by solar heating. Even though the sunlight at Triton is extremely faint, it is enough to warm dark material beneath the transparent nitrogen ice, vaporizing the nitrogen and building pressure until it erupts. Triton's surface is young with few craters, suggesting it has been resurfaced recently, perhaps by cryovolcanism, where water and ammonia mixtures erupt like lava, smoothing over older features and creating the bright, icy plains Voyager observed. The moon also has a cantaloupe terrain, a region covered in dimples and ridges that looks like the skin of a melon, and this unusual texture may have formed from repeated melting and refreezing of the surface over billions of years. Triton's capture by Neptune was a violent event, probably disrupting any other moons that existed at the time, and the tidal heating from that capture may have melted Triton's interior, allowing it to differentiate into a rocky core and an icy mantle. The moon's orbit is circular now, but it was probably highly elliptical immediately after capture, and the circularization process released enormous amounts of heat, possibly creating a subsurface ocean that may still exist today beneath the frozen crust. If Triton has a subsurface ocean, it could potentially harbor life, though the conditions would be extreme, and any life would have to survive on chemical energy rather than sunlight, similar to life near hydrothermal vents on Earth. But Voyager could not detect a subsurface ocean. It could only reveal Triton's surface, and the question of what lies beneath remains open, waiting for a future mission to return and explore this distant moon in greater detail. Neptune has other moons, though most are small and faint, and Voyager discovered 6 new ones, bringing the total to 8 at the time, and later observations from Earth have found more, bringing the current count to 14. The largest of the other moons is Proteus, an irregular chunk of rock and ice about 420 kilometers across, heavily cratered and shaped by impacts, and it orbits closer to Neptune than Triton does. The smaller moons are probably captured asteroids or comets, or fragments from collisions, and they orbit in the outer reaches of Neptune's gravitational influence, some in retrograde orbits, like Triton. Neptune also has rings, faint and dark, discovered from Earth before Voyager arrived, and the spacecraft confirmed they are complete rings, though some sections are clumpy, creating arcs rather than continuous circles. The rings are made of dark particles, probably containing carbon compounds, and they are much fainter than Saturn's rings, barely visible even in Voyager's images, and they are named after astronomers who studied Neptune, Galley, Leverrier, Lassell, and Adams. The clumpy arcs in the Adams ring were puzzling, because orbital mechanics suggests they should spread out into continuous rings over time, but small moons shepherd the material, keeping the arcs confined through gravitational resonances. Voyager discovered several shepherd moons, tiny irregular objects, only tens of kilometers across, and their gravity shapes the rings, creating gaps, waves, and the clumpy arcs that make Neptune's ring system unique. The rings are probably young, maybe only millions of years old, and they may be constantly renewed by material knocked off the inner moons, creating a dynamic system that evolves over time. After the encounter with Neptune and Triton, Voyager 2 had no more planets to visit, its trajectory carrying it below the plane of the solar system and outward toward interstellar space. The spacecraft had completed the grand tour, visiting all 4 giant planets, discovering new moons and rings, and revolutionizing our understanding of the outer solar system in ways that are still being absorbed decades later. The mission had lasted 12 years so far, but the spacecraft was still healthy, its power supply still functioning, and its instruments still sending data. So NASA extended the mission into a new phase called the Voyager interstellar mission. The goal now was to study the edge of the sun's influence, the boundary where the solar wind meets the interstellar medium, and to measure the properties of space beyond the planets, a region no spacecraft had ever reached. Imagine watching Neptune shrink behind you, the blue planet becoming smaller and dimmer, its storms and clouds fading into a single point of light, and knowing that you will never return, never see it again. Triton would also disappear, its geysers and icy plains invisible, and you would be alone in the darkness, with only the distant stars ahead and the fading glow of the sun behind, a tiny yellow star among countless others. Voyager 2 carried that view in its cameras, and it sent the final images back to Earth, the last close-up pictures of Neptune and Triton frozen in time, a record of the encounter that will last as long as the data survives. And then the spacecraft moved on, coasting through the outer solar system, heading toward the boundary, and carrying the golden record farther than any message from Earth has ever traveled. On February 14, 1990, 6 months after leaving Neptune, Voyager 1 was commanded to turn its camera back toward the inner solar system and to take one last look at the planets it had left behind. The spacecraft was 6 billion kilometers from Earth, beyond the orbit of Neptune, and at that distance the Sun was just a bright star and Earth was a tiny speck, barely visible, caught in a beam of scattered sunlight. The image became known as the pale blue dot, and it showed Earth as a single pixel, suspended in the vastness of space, a fragile mote of dust in the cosmic dark, and it changed how we see ourselves. Carl Sagan, who had advocated for taking the image, wrote about it eloquently, reflecting on the significance of seeing our entire world reduced to a pale blue point, everything we have ever known contained in that tiny speck. The pale blue dot is humbling, because it shows how small we are, how vast the universe is, and how fragile our world looks from the perspective of deep space. Every human who has ever lived, every war, every discovery, every triumph and tragedy, all of it happened on that pale blue dot, a world so small it nearly disappears when seen from the outer solar system. The image reminds us that Earth is our only home, at least for now, and that we must take care of it, because there is nowhere else to go, no other planet within reach that could sustain us if we destroy this one. It also reminds us of our connection to the cosmos, that we are part of something larger, and that exploring space is not just about discovering new worlds, but about understanding our place in the universe. Voyager 1 took images of other planets too: Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, all of them visible as tiny points of light arranged in a family portrait that captured the solar system from an outside perspective. Mercury was too close to the Sun to photograph safely, and the glare would have damaged Voyager's cameras, so it was left out, but the other planets were there, small and distant, scattered across the frame. The images were sent back to Earth, taking more than 5 hours to arrive, and they were processed and assembled into a mosaic, a final portrait of the solar system from the edge, a view no one had seen before. After taking the images, Voyager 1's cameras were shut off permanently to conserve power, and because there would be nothing more to photograph, and the spacecraft would never take another picture for the rest of its journey. The pale blue dot became an iconic image, reproduced in books, posters, and documentaries, and it has inspired countless people to think about the fragility of Earth and the importance of space exploration. It is a reminder that our world is tiny, but it is also precious, and that the act of looking back, of seeing ourselves from afar, is an act of perspective and wisdom. Voyager's mission had been to explore the outer planets, but in taking that final image, it gave us something more, a gift of perspective, a way of seeing Earth that changes how we think about our place in the cosmos. The image is a farewell, Voyager saying goodbye to the solar system, looking back one last time before continuing its journey into the darkness, carrying the golden record toward the stars. Imagine being on Voyager, billions of kilometers from Earth, turning your camera back toward the Sun and seeing the planets as tiny dots of light, so small and faint they barely register, and knowing that one of those dots is home. You would feel the distance, the vast emptiness separating you from everything familiar, and you would understand that space is not just big, it is incomprehensibly vast, and the distances between worlds are almost beyond imagining. But you would also feel a connection, a thread linking you back to Earth, invisible but real, a shared origin, a shared history, and the knowledge that someone on that pale blue dot is listening for your signal. Voyager carried that connection with it, in the form of radio waves, signals sent back to Earth, and in the golden record, a physical message, a handshake across time, a reminder that we are here, and we reached out. After taking the pale blue dot image, Voyager 1 continued outward, leaving the planets behind and entering the realm of comets, the Kuiper Belt, and the scattered disk, though it would not encounter any objects there, only emptiness. The spacecraft's trajectory carried it above the plane of the solar system, and it was moving at about 17 kilometers per second, fast enough to escape the sun's gravity and never return, destined to wander the galaxy forever. Voyager 2 followed a similar path below the plane, also moving fast enough to escape, and both spacecraft were now on trajectories that would take them out of the solar system and into interstellar space, a journey that would take decades. The mission entered a new phase, focused on measuring the solar wind, cosmic rays, and the properties of space at the edge of the sun's influence, and waiting for the moment when the spacecraft would cross the boundary into interstellar space. The pale blue dot was the last time Voyager looked back, and from that moment on, the spacecraft faced forward, toward the unknown, toward the stars, and toward a future that would stretch billions of years into the distance. Earth continued to orbit the sun, the pale blue dot turning through space, and life continued, unaware that a small machine far away had captured an image that would change how we see ourselves. The image is a gift from Voyager to humanity, a perspective we could not gain without leaving Earth, and a reminder that exploration is not just about discovery, but about understanding who we are and where we stand in the universe. And so Voyager moved on, carrying the golden record farther from Earth, farther from the sun, and deeper into the cold darkness where starlight is the only illumination and the void stretches endlessly in all directions. The sun creates a bubble around itself called the heliosphere, a region where the solar wind, a stream of charged particles flowing outward from the sun, dominates the environment and pushes back against the interstellar medium. The solar wind travels at about 400 kilometers per second, carrying magnetic fields and energy outward, and it extends far beyond the planets, creating a protective cocoon that shields the solar system from some galactic cosmic rays. The boundary of the heliosphere is not sharp. It is a transition region where the solar wind slows, compresses, and eventually merges with the interstellar medium. And this boundary has several layers, each with different physical properties. The first layer is the termination shock, where the solar wind slows from supersonic to subsonic speeds, and beyond that lies the helios sheath, a turbulent region, where the slowed solar wind mingles with the interstellar medium. The outermost boundary is the heliopause, the point where the solar wind's pressure balances the pressure of the interstellar medium, and beyond this boundary, the spacecraft is truly in interstellar space, though still within the sun's gravitational influence. Voyager 1 crossed the termination shock in December 2004, about 94 astronomical units from the sun, and the spacecraft detected a sudden increase in the magnetic field and a decrease in the speed of the solar wind particles. The crossing was not smooth, the boundary moved back and forth, and Voyager crossed it several times as the solar wind pressure fluctuated, but eventually the spacecraft moved fully into the helios sheath and continued outward. Voyager 2 crossed the termination shock in August 2007, about 84 astronomical units from the Sun, closer than Voyager 1, showing that the heliosphere is not symmetrical, probably distorted by the Sun's motion through the galaxy. Both spacecraft then spent years traveling through the helios sheath, a strange region where the solar wind is turbulent, mixing with the interstellar medium, and where cosmic rays from outside the solar system begin to dominate over particles from the Sun. The helios sheath is thick, about 40 to 50 astronomical units, and it took Voyager 1 nearly 8 years to cross it, finally reaching the heliopause in August 2012, becoming the first human-made object to enter interstellar space. The crossing was marked by a sudden drop in solar wind particles, and a corresponding increase in galactic cosmic rays, high-energy particles that originate from supernova explosions and other violent events throughout the galaxy. The magnetic field also changed, no longer dominated by the Sun's field, but now reflecting the interstellar field. And this shift confirmed that Voyager 1 had truly left the heliosphere and entered a new realm. Voyager 2 crossed the heliopause in November 2018, about 119 astronomical units from the Sun, and it confirmed Voyager 1's observations, showing that the boundary is real and measurable, though it moves and shifts with changes in the solar wind. The two spacecraft crossed at different distances and in different directions, and their measurements revealed that the heliopause is not a perfect sphere. It is shaped by the Sun's motion through the galaxy and by variations in the interstellar medium. The interstellar medium itself is not uniform. It has clumps, clouds, and voids, and the heliosphere moves through this medium like a ship through water, creating a bow shock ahead of the Sun and a tail stretching behind. Both spacecraft are now in interstellar space, but they are still within the Sun's gravitational influence, and they will remain so for tens of thousands of years until they finally escape into the wider galaxy. Interstellar space is not empty. It contains gas, mostly hydrogen, at a density of about 1 atom per 10 cubic centimeters, far more tenuous than the best vacuum we can create on Earth, but denser than the solar wind in the heliosphere. The temperature of the interstellar medium is about 15,000 degrees Celsius, but because the density is so low, there is very little heat energy, and a spacecraft in interstellar space would actually be very cold, losing heat through radiation. The magnetic field in interstellar space is weak, about 1/1,000,000th of the strength of Earth's magnetic field, but it is organized on galactic scales, threading through the galaxy and shaping the flow of cosmic rays and charged particles. Voyager's instruments measure the magnetic field, the density of particles, and the flux of cosmic rays, and this data is sent back to Earth, providing the first direct measurements of interstellar space from within. The signals from Voyager take more than 20 hours to reach Earth now, traveling at the speed of light across billions of kilometers, and the spacecraft are so far away that their signals are incredibly faint, requiring the largest radio dishes on Earth to detect them. The Deep Space Network continues to track both spacecraft, listening for their signals and sending commands when needed, though the commands are rare now, mostly instructions to manage the dwindling power supply and shut down non-essential systems. The spacecraft are receding at about 3.6 astronomical units per year, or about 17 kilometers per second, and this speed is constant because there is no air resistance or friction in space, and the spacecraft will coast at this speed forever. Every year, Voyager moves about 500 million kilometers farther from Earth, and the signals take a little longer to arrive, a reminder of the relentless expansion of distance, the growing gap between the spacecraft and home. Crossing the heliopause was a milestone, a moment celebrated by scientists and space enthusiasts worldwide, because it marked the beginning of true interstellar exploration, a human-made object reaching beyond the Sun's domain. But the crossing was also quiet, just a change in numbers, a shift in the data, and the spacecraft did not know or care that it had achieved something historic. It simply continued its journey, following the laws of physics. For Voyager, there is no finish line, no destination, only the endless journey through space, measuring, recording, and transmitting data back to Earth as long as the power lasts. And when the power finally runs out, the spacecraft will go silent, but it will continue moving, carrying the golden record deeper into the galaxy, a message that will outlast the civilization that sent it. The interstellar medium is the gas and dust that fills the space between stars, and Voyager is now measuring it directly, providing the first in situ data about the conditions in our local region of the galaxy. The medium is mostly hydrogen, the most common element in the universe, with traces of helium and heavier elements, and it exists in different phases: cold clouds, warm diffuse gas, and hot ionized regions depending on local conditions. Voyager is traveling through a region called the local interstellar cloud, a small cloud of warm gas about 30 light-years across, and this cloud is part of a larger structure called the local bubble, a cavity carved out by ancient supernova explosions. The local bubble is about 300 light-years across, filled with hot, tenuous gas, and it is surrounded by denser clouds where stars are forming, and Voyager will remain in this bubble for thousands of years before potentially entering a denser region. The density of the interstellar medium is incredibly low, about 1 hydrogen atom per 10 cubic centimeters in the local interstellar cloud, and this is far lower than any vacuum we can create in laboratories on Earth. Despite the low density, the total mass of the interstellar medium is substantial, accounting for about 10 to 15% of the visible matter in the galaxy, and it plays a crucial role in star formation and the chemical evolution of the galaxy. The temperature of the gas around Voyager is about 15,000 degrees Celsius. But because the density is so low, the gas carries very little heat energy, and Voyager is not warmed by it, instead cooling through radiation into space. The gas is ionized, meaning the hydrogen atoms have lost their electrons, and the free electrons interact with the spacecraft, creating a plasma environment that Voyager's instruments can measure. The magnetic field in the interstellar medium is weak, but it plays an important role in shaping the flow of charged particles, and Voyager measures the field strength and direction as it travels, revealing how the field is structured in our local region. The field is probably aligned with the spiral arm of the galaxy, threading through the disk and connecting different regions, and it may help funnel cosmic rays and influence the formation of stars. Cosmic rays are high-energy particles, mostly protons, that travel through the galaxy at nearly the speed of light, and they are created by supernova explosions, pulsars, and other violent events, and they pervade the interstellar medium. Voyager detects an increase in cosmic rays, now that it is outside the heliosphere because the solar wind no longer shields the spacecraft, and the measurements reveal the spectrum and intensity of these particles in interstellar space. The interstellar medium is not static. It is stirred by stellar winds, supernova shockwaves, and the rotation of the galaxy, creating a dynamic environment where gas flows, compresses, and heats in response to energy input. Supernova explosions create bubbles of hot gas, expanding outward and compressing the surrounding medium, and these bubbles can merge to create larger structures like the local bubble, cavities that persist for millions of years. When gas is compressed, it can become dense enough to collapse under its own gravity, forming molecular clouds where new stars are born, and this process connects the life cycle of stars to the structure of the interstellar medium. Voyager is measuring the raw material for future star formation, the gas and dust that will eventually condense into new stars, planets, and, perhaps life, billions of years from now. The spacecraft is also measuring dust grains, tiny particles smaller than a micrometer made of carbon, silicates, and ices, and these grains are important for understanding how elements are distributed in the galaxy. Dust grains are created in the atmospheres of dying stars, and they are scattered into space by stellar winds and supernova explosions, and they carry heavy elements like carbon, oxygen, and iron into the interstellar medium. The grains can collide with Voyager, and the spacecraft detects these impacts using its plasma wave instrument, which registers the tiny bursts of charged particles created when a dust grain hits the spacecraft at high speed. By counting the impacts, scientists can estimate the density of dust and the size distribution of the grains, providing information about the structure of the interstellar medium that cannot be obtained from Earth-based observations. Voyager's measurements are unique because the spacecraft is actually there, in interstellar space, experiencing the environment directly, rather than observing it from Earth through telescopes that can only see light and other radiation. The data sent back to Earth is sparse, because the power is limited and the instruments are old, but every measurement is precious, revealing details about the interstellar medium that will inform our understanding of the galaxy for decades. The spacecraft is also measuring how the Sun's influence extends into interstellar space by tracking the boundary of the heliosphere and watching how it responds to changes in the solar wind, revealing the dynamic interaction between the Sun and the galaxy. This data helps scientists model the heliosphere, predict how it will change in the future, and understand how the Sun protects the solar system from cosmic rays, a question with implications for space weather and the safety of future astronauts. Imagine drifting through the interstellar medium, surrounded by an incredibly thin gas, so tenuous you would never notice it, but vast and ancient, stretching between the stars and filling the galaxy. You would see stars in all directions, some bright, some faint, but all of them distant, light years away. And you would know that the space between them is not empty, it is filled with gas, dust, and energy, a living medium that connects the galaxy. The Sun would be behind you, a bright yellow star, one among billions, and you would see the heliosphere as a faint bubble, invisible except for the way it deflects the interstellar wind, a small shelter in the vastness of space. And you would feel the loneliness, the isolation, the knowledge that you are farther from home than anyone has ever been, drifting through a realm where human voices are silent and the only sounds are the whisper of cosmic rays and the hum of your instruments. Voyager is a marvel of engineering, built in the 1970s with technology that now seems primitive, yet still functioning after more than 45 years in space, farther from Earth than any other human-made object. Each spacecraft weighs about 820 kilograms, about the size of a small car, and it is built around a 10-sided bus that houses the electronics, computers, and power systems, with instruments mounted on booms and platforms extending outward. The most recognizable feature is the large dish antenna, 3.7 meters in diameter, which points back toward Earth and is used to send and receive signals, and it is protected by a white sun shield that keeps the spacecraft cool. The computers on Voyager are ancient by modern standards, with less memory than a simple calculator, but they are robust and radiation hardened, designed to survive decades in space without maintenance or repair. The power source is a radioisotope thermoelectric generator, or RTG, which converts heat from decaying plutonium into electricity, and it has no moving parts, making it extremely reliable, though the power output decreases slowly over time as the plutonium decays. At launch, each RTG provided about 470 watts, enough to power a few light bulbs, and now, more than 45 years later, the power output has dropped to about 220 watts, and it continues to decline by about 4 watts per year. This declining power is the limiting factor for Voyager's mission, because as the power drops, instruments must be shut off to conserve energy, and eventually there will not be enough power to operate any instruments or transmit signals back to Earth. Mission engineers have carefully managed the power budget, turning off heaters, shutting down instruments that are no longer critical, and prioritizing the most important measurements, squeezing every last year of operation from the fading power supply. The instruments on Voyager were designed to study the planets, but many of them continue to function in interstellar space, measuring magnetic fields, charged particles, cosmic rays, and plasma waves, providing data about the environment beyond the heliosphere. The magnetometer measures the strength and direction of magnetic fields, and it has been operating continuously since launch, providing a 45-year record of the magnetic environment from Earth to interstellar space. The cosmic ray instrument detects high-energy particles from outside the solar system, and it has measured the increase in cosmic rays as Voyager crossed the heliopause, confirming that the spacecraft is in interstellar space. The plasma wave instrument detects oscillations in the surrounding plasma, and it has measured the density and temperature of the interstellar medium, as well as detecting impacts from dust grains hitting the spacecraft. Communication with Voyager is a challenge because of the enormous distance. Signals take more than 22 hours to reach Voyager 1 and about 18 hours to reach Voyager 2, traveling at the speed of light across billions of kilometers. The signals from the spacecraft are incredibly faint, only about 20 watts of power when they leave Voyager, and by the time they reach Earth, they are a billion times weaker, barely detectable even with the largest radio dishes. The Deep Space Network uses 3 massive radio antennas, each 70 meters in diameter, located in California, Spain, and Australia, and these dishes track Voyager around the clock, ensuring that no matter where Earth is in its rotation, one dish is always listening. The data rate from Voyager is extremely low, only about 160 bits per second, slower than the earliest dial-up modems. But even this slow trickle of data is precious, carrying measurements from the edge of the solar system and beyond. Commands sent to Voyager must be carefully planned, because the long communication delay means it takes more than a day to send a command and receive confirmation that it was executed, and any mistake could shut down the spacecraft or damage its systems. The engineers who operate Voyager today were not born when the spacecraft launched, but they have learned from their predecessors, studying the systems, the history, and the quirks of the spacecraft, becoming caretakers of a machine older than themselves. The software on Voyager has been updated many times over the years, with patches and fixes uploaded from Earth, and the spacecraft is far more capable now than it was at launch, despite the aging hardware and declining power. Every command, every update, every decision is made with care, because Voyager cannot be repaired, and once the power runs out, the spacecraft will go silent forever. So every year of operation is a gift, a bonus beyond the original mission. The spacecraft's attitude control system keeps the antenna pointed at Earth, using small thrusters that fire periodically to correct the orientation, and the thrusters run on hydrazine fuel, which is also slowly running out after decades of use. The spacecraft must remain pointed at Earth to communicate, and if the attitude control fails, the signal will be lost, and Voyager will drift silently without any way to receive commands or transmit data. Engineers have switched to backup thrusters that have not been used in decades, firing them successfully after 37 years of dormancy. And this clever workaround has extended Voyager's operational life by years, conserving the primary thrusters for later use. Every system on Voyager is aging. The electronics are exposed to cosmic radiation, the mechanical parts are stressed by temperature cycles, and yet the spacecraft continues to function, a testament to the quality of its design and construction. The golden record is mounted on the side of each spacecraft, protected by its aluminum cover, and it has remained sealed since launch, undamaged by radiation, temperature extremes, or the occasional dust grain impact. The record contains its message, sounds, music, and images from Earth, and it will remain readable for billions of years, long after Voyager's electronics have failed and its power has run out. The spacecraft will carry the record through interstellar space, drifting silently, and if it is ever found, the finder will know that intelligent life exists somewhere in the galaxy, or at least that it existed once, billions of years ago. But the record is not the only message Voyager carries. The spacecraft itself is a message, a demonstration of human ingenuity, curiosity, and the desire to reach beyond our world, to explore, to learn, and to connect with the cosmos. Imagine being Voyager, a small machine alone in the darkness, your power slowly fading, your instruments one by one shutting down, and knowing that you will never return, never be repaired, and never see Earth again. You would continue anyway, because that is your purpose, to travel, to measure, to send data back as long as you can, and then to drift silently, carrying your message into the unknown future. You would feel the cold of space, the faint warmth from your decaying plutonium, the only heat source in the void, and you would watch the stars slowly shift as you move through the galaxy, a journey measured in millennia, and you would carry the voices of Earth, the music, the laughter, the greetings in 55 languages, a reminder that you came from somewhere, that you were built with care, and that you carry the hopes of a species that dared to reach for the stars. The power from Voyager's RTG will continue to decline, and by the mid-2020s, probably around 2025 to 2030, there will not be enough electricity to power any instruments or maintain communication with Earth. Mission engineers are planning for this moment, deciding which instruments to shut down first, and which to keep running until the very end, prioritizing the measurements that will provide the most valuable data from interstellar space. The plasma wave instrument may be the last to operate because it uses very little power and provides unique data about the interstellar medium, and it will continue to measure oscillations in the plasma until the power drops below the minimum threshold. When the power finally runs out, Voyager will go silent. No more signals, no more data, just a sudden absence where once there was a faint whisper from the edge of the solar system. The last signal from Voyager will be received on Earth, traveling for more than 22 hours across billions of kilometers. And when it arrives, scientists will know that the mission has ended, that the spacecraft is now truly alone. There will be no fanfare, no dramatic moment, just a missing signal, an expected silence, and the knowledge that Voyager has finally exhausted its power after more than 50 years of continuous operation. The spacecraft will continue to move, coasting at 17 kilometers per second, but it will be blind and deaf, unable to measure its surroundings or report back, and it will drift through the galaxy like a ghost, invisible except to anyone who happens upon it. The antennas on Earth will listen for a while, hoping for one more signal, one last whisper, but eventually they will move on, tracking other missions, other spacecraft, and Voyager will be left behind, alone in the dark. Engineers and scientists who have worked on Voyager for decades will feel the loss because the mission has been part of their lives, a constant presence, a source of wonder and discovery, and its end will mark the close of an era in space exploration. But Voyager's legacy will endure in the data it collected, the images it sent back, the discoveries it made, and the inspiration it provided to generations of scientists, engineers, and dreamers who looked up and wondered what lies beyond. The mission transformed our understanding of the outer solar system, revealing Jupiter's volcanic moon Io, Saturn's intricate rings, Uranus's tilted axis, Neptune's dark storms, and finally the boundary between the Sun's domain and interstellar space. Voyager proved that robotic exploration is possible, that machines can travel farther than humans, survive for decades in harsh environments, and return data that changes how we see the universe, and that legacy will inform every future mission to the outer planets and beyond. After the power runs out, Voyager will continue its journey, unaware, unchanging, and silent, following the trajectory set by its planetary encounters, and it will never deviate from that path unless it collides with something, which is vanishingly unlikely. The spacecraft will travel through interstellar space for thousands of years, drifting past other stars, though always at great distances, never close enough to be captured by gravity or significantly deflected from its course. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis, and it will be the closest approach to another star that Voyager will make for hundreds of thousands of years. Voyager 2 will pass near the star Ross 248 in about 40,000 years, and then near Sirius, the brightest star in our sky, in about 296,000 years, though still at a distance of several light-years, too far to notice. The spacecraft will never stop, never slow down, unless it collides with something large enough to destroy it, and the chances of such a collision are infinitesimally small. So Voyager will probably survive for billions of years, outlasting the Earth itself. The Sun will eventually expand into a red giant in about 5 billion years, swallowing Mercury, Venus, and possibly Earth, but Voyager will be far away, untouched by the Sun's death throes, continuing its journey through the galaxy. The galaxy itself will change. Stars will form and die. The spiral arms will shift, and the Sun will complete many orbits around the galactic center, but Voyager will continue to move, a tiny mote drifting through the vastness. Eventually, trillions of years from now, the stars will burn out, the galaxy will go dark, and the universe will enter an era dominated by black holes, and even then, Voyager will still be traveling, unchanged, carrying the golden record through the cold darkness. The golden record will outlast everything. The spacecraft, the electronics, the power source, all of it will eventually decay, but the record itself, protected by its aluminum cover, will remain intact for billions of years. The record's gold plating will not tarnish in space, because there is no oxygen, and the information encoded on its surface will remain readable, assuming anyone or anything finds it and understands how to play it. If the record is found, it will be in the distant future, millions or billions of years from now, by a civilization so advanced they may barely recognize the technology, but they will understand the intention, a message from a distant world. The sounds, the music, the images will tell them about Earth, about humans, about life in the late 20th century, a snapshot of a moment in time, preserved forever in metal and sent into the galaxy as a gift. But the chances of the record ever being found are incredibly small. Space is vast, and Voyager is tiny, and it is not traveling toward any particular star, just drifting through the galactic disk, following the laws of motion. The record is more symbolic than practical, a message sent with hope, but no expectation of reply, an act of faith that somewhere, somewhen, someone will find it and know that we existed. It is a message to ourselves as much as to others, a reminder that we are curious, creative, and bold, and that we are willing to reach out into the unknown, even if the message takes billions of years to arrive. And so Voyager will carry the record forever, through the dark, through the ages, through the slow turning of the galaxy, a message from Earth, a greeting from humanity, drifting endlessly through the cosmos. In 40,000 years, Voyager 1 will make its closest approach to another star, Gliese 445, passing within about 1.6 light-years, close enough that if that star has planets, intelligent beings there might detect Voyager with advanced telescopes. But Voyager will not stop. It will sweep past at 17 kilometers per second, a brief visitor from another star system, and if no one is watching, it will pass unnoticed, continuing on its journey through the galaxy. The spacecraft will be cold by then, its power long exhausted, its instruments silent, and the only sign of its human origin will be the golden record, sealed in its aluminum cover, waiting to be discovered. If Gliese 445 has a civilization, they might find Voyager centuries or millennia later, studying the record and learning about a distant world called Earth, a place they have never seen and may never visit. In 296,000 years, Voyager 2 will pass near Sirius, the brightest star in our night sky, at a distance of about 4.3 light-years, far enough that it will be invisible to any observers there. Sirius is a binary system, a bright blue-white star and a faint white dwarf, and it is one of the closest stars to Earth. But Voyager will not linger. It will continue past, moving deeper into the galaxy. By that time, the constellations we know will have changed, the stars drifting through space on their own orbits, and the patterns familiar to us today will be unrecognizable, distorted by the motion of the stars over hundreds of thousands of years. The Sun will be just another star, faint and distant from Voyager's perspective, lost among billions of others, and the spacecraft will have no way to identify its home, no way to remember where it came from. In 1,000,000 years, Voyager will be deep in the galactic disk, far from the solar system, surrounded by stars that are strangers, and it will have encountered none of them closely, just passed them at distances measured in light years. The spacecraft will be ancient, older than most mountains on Earth, older than many species, and it will have outlasted empires, civilizations, and perhaps even humanity itself if we do not survive or if we leave Earth for other worlds. The golden record will still be intact. The voices still encoded in its grooves, the music still waiting to be played, and the images still hidden in the audio tracks, a time capsule from a world that may no longer exist. If Earth has been destroyed by then, by war, by climate change, by an asteroid impact, or by the sun's expansion, the record will be the only proof that we ever existed, the last whisper of a vanished species. But if humanity survives and spreads through the galaxy, if we build starships and colonize other worlds, we might find Voyager someday, centuries or millennia from now, and bring it home as a relic from the early space age. We might place it in a museum, restored and displayed, the golden record played for visitors who want to hear the voices of their ancestors, the sounds of a world that is now unrecognizable after thousands of years of change. Or we might leave it where it is, continuing its journey, because Voyager's purpose was never to return. It was to explore, to reach beyond, and to carry our message into the unknown, and that purpose is best served by letting it go. In 1 billion years, the galaxy will have changed dramatically. Stars will have formed and died. The spiral arms will have shifted, and the sun will have orbited the galactic center 4 or 5 times. carrying Earth and the other planets with it. Voyager will still be moving, still carrying the record, and the chance of it being found remains vanishingly small, but not zero, and that tiny chance is enough to make the message meaningful. In 5 billion years, the Sun will become a red giant, swelling to consume the inner planets, and Earth may be destroyed, its oceans boiled away, its atmosphere stripped, its surface melted into a lifeless cinder. But Voyager will be far away, unaffected by the Sun's death, continuing its journey through the galaxy, and the record will survive, carrying the sounds and images of a world that no longer exists, a memorial to a planet that once was home. In 10 billion years, the Sun will be a white dwarf, cooling slowly, and the solar system will be dark and cold, and Voyager will still be traveling, unchanged, eternal, a relic from an age when stars still burned. Eventually, trillions of years in the future, the last stars will burn out. The universe will enter an era of black holes and cold remnants, and the galaxy will be a dark, quiet place, with no new stars forming and no light except the faint glow of radiation from black holes. Voyager will still be there, drifting through the darkness, its golden record intact, though there will be no one left to find it, no civilizations, no life, just the cold remnants of what once was. The record will remain readable for billions more years, perhaps until the protons in the gold atoms decay, an event so far in the future it is almost beyond comprehension, and even then, some trace of the message may remain. Voyager's journey is eternal. It will never end unless the universe itself ends, and even then, the spacecraft may persist, a monument to the audacity of a species that dared to send a message into the infinite future. But perhaps the message will be found earlier, in the next few million years, by a civilization we cannot imagine, a species that has mastered space travel and explores the galaxy, searching for signs of other intelligent life. They might find Voyager by chance, detect it with their sensors, intercept it, and bring it aboard their vessel, and they will study the record, decode the images, and listen to the sounds, and they will know that they are not alone. They will hear our voices, our music, our laughter, and they will see our world, blue and green, covered in oceans and continents, and they will understand that we reached out, that we tried to connect, even knowing we might never receive an answer. And that understanding will be Voyager's greatest gift, not the data it collected, not the discoveries it made, but the message it carries, a message of hope, curiosity, and the desire to reach beyond ourselves and connect with the unknown. We return now to Earth, to the present moment, where Voyager's signal still reaches us, faint but steady, a whisper from the edge of the solar system, reminding us that the mission continues even as the power slowly fades. Voyager is farther from us than any other human-made object, more than 24 billion kilometers away, and yet we can still hear it, still receive its data, still know that it is out there traveling onward. The mission has lasted more than 45 years, far longer than anyone expected, and it has transformed how we understand the solar system, revealing worlds we had only glimpsed and showing us the beauty and complexity of the outer planets. Jupiter's volcanic moon Io, Saturn's intricate rings, Uranus's tilted axis, Neptune's dark storms, all of these discoveries came from Voyager, and they have shaped planetary science for generations, inspiring new missions and new questions. But Voyager is more than a scientific mission. It is also a statement about who we are, what we value, and what we hope to achieve. And the golden record is the heart of that statement. A message sent with no guarantee of reply. The record represents our best selves, our creativity, our diversity, our desire to connect, and it says that we exist, that we are curious, and that we are willing to reach out into the unknown, even if it takes billions of years for our message to be heard. In a world often divided by conflict, the record is a unifying vision, a reminder that we are one species on one small planet, and that our differences are small compared to the vastness of space and the challenges we face together. The act of sending the record was an act of hope, a bet that intelligence exists elsewhere, that the universe is not empty, and that someday, somewhere, someone will find our message and know that we were here. We do not know if that will ever happen. The universe is vast and Voyager is tiny, and the chances of it being found are incredibly small, but the act of sending it matters, regardless of the outcome. It matters because it shows we are willing to try, to reach beyond our world, to communicate across the gulf of space and time, and to say that we are here, we are alive, and we are thinking about you, whoever you are. The pale blue dot image, taken by Voyager 1 in 1990, is another gift from the mission, a perspective that changes how we see ourselves, showing Earth as a tiny speck in the vastness of space. That image reminds us of our fragility, that Earth is our only home, at least for now, and that we must take care of it, because there is no backup, no other planet we can flee to if we destroy this one. Voyager also reminds us of what we can achieve when we work together. The mission was the result of thousands of people, engineers, scientists, technicians, all contributing their skills and knowledge to build something greater than any individual. The spacecraft is a testament to human ingenuity, designed with 1970s technology, yet still functioning after more than 45 years, surviving radiation, temperature extremes, and the harsh environment of space without maintenance or repair. The mission was planned with care and foresight, taking advantage of a rare planetary alignment, using gravity assists to visit all 4 giant planets, and designing the spacecraft to last far longer than the primary mission required. And it worked, better than anyone hoped. Voyager not only completed its planetary tour, but it continued onward, entering interstellar space and sending back data from a realm no spacecraft had ever reached before. We learned from Voyager that exploration is possible, that we can send machines to the farthest reaches of the solar system, that we can communicate across billions of kilometers, and that we can discover worlds we had never seen up close. We learned that the outer planets are not cold, dead worlds, but dynamic environments with weather, moons, and complex systems shaped by gravity, heat, and time. And each planet tells a story about how the solar system formed and evolved. We learned that interstellar space is not empty, but filled with gas, dust, cosmic rays, and magnetic fields, a medium that connects the stars and shapes the galaxy, and Voyager is giving us our first direct measurements of that environment. And we learned that humans are explorers, that we are driven to know what lies beyond, to push the boundaries of the known, and to reach for the stars, even if we can only send our machines while we remain behind. Voyager will eventually go silent, the power will run out, and the signals will cease, and that day is coming soon, perhaps in the next few years, but the mission will not truly end because the spacecraft will continue to travel. Long after the last signal is received, Voyager will still be moving, carrying the golden record farther from Earth, and the message will endure, waiting for a finder that may never come, but waiting nonetheless. The mission has given us so much: knowledge, inspiration, perspective, and hope, and when it finally ends, we will feel the loss. but we will also celebrate what was achieved, and we will remember that Voyager showed us what is possible. We will remember the images, the Great Red Spot, the rings of Saturn, the geysers of Triton, the pale blue dot, all of them moments captured by a small machine far from home and sent back to us across the darkness. We will remember the scientists and engineers who built Voyager, who guided it through the solar system, and who have kept it running for decades, passing their knowledge to the next generation, ensuring the mission continues as long as possible. And we will remember the message, the golden record, the sounds and music and images from Earth sent into the void with hope and humility, a greeting from humanity to the unknown cosmos. Voyager is not just a spacecraft. It is a symbol of what we can achieve when we are curious, when we work together, and when we dare to reach beyond ourselves, and that symbol will endure long after the mission ends. So tonight, as you drift towards sleep, think of Voyager, still traveling, still moving away from Earth, and know that somewhere out there, far beyond the planets, our message is carried onward into the galaxy. Imagine Voyager in the darkness, its antenna pointed toward a sun that has become just another star, sending signals that take hours to reach home, and knowing that soon the power will fade and the signals will stop. The spacecraft will continue silently, coasting through the interstellar medium, past stars we have never seen, through regions we can only imagine, and it will carry the voices of Earth into the infinite future. The golden record will remain sealed, the sounds and images preserved, waiting for someone, somewhere, somewhen, to find it and play it, and to hear the message we sent so long ago from a pale blue dot. And if no one ever finds it, if the record drifts through the galaxy forever, unheard and unseen, then it will still have meaning because it was sent with love, with hope, and with the simple desire to say we were here. So rest now, knowing that Voyager continues its journey, that the mission has been a triumph, and that humanity has reached beyond its world to touch the stars, even if only with a small machine carrying a golden record. The spacecraft will outlive us all, traveling long after Earth has changed beyond recognition, long after the sun has died, and perhaps even long after the last stars have burned out, a silent witness to the passage of time. But tonight, the mission is still active. The signals still arrive, the data still flows, and we are still connected to Voyager, a thread of light spanning billions of kilometers, linking us to our most distant ambassador. Sleep well and know that somewhere in the darkness, far beyond the reach of sunlight, our message is traveling onward, carried by Voyager, the last messenger from Earth, journeying endlessly toward the stars.